Right. So proving 3 implies 1 is actually pretty straightforward, right? So let's just pick up the F flow such that there exists no augmenting paths, right? So we want a flow such that the condition 3 holds, right? When the condition 3 holds, right, so we can sort of like imagine there's a flow and this is the associated residual graph, right? Right. So now let's imagine this is the residual graph, right? And I want to run. Let's also run a search, right? Let's call that. Let's run a BFS, starting from S, right? So when I run BFS starting from S on this residual graph, what I'm going to expect to see is that T is not reachable, right? So if T were reachable, then I were able to find a path that's connecting from S to T. That basically means that the augmenting path exists, right? So because augmenting path doesn't exist, we expect to see that T is not reachable from S, right? So this is the first observation we have, right? So when T is not reachable from S, we sort of can imagine that let's put together all the nodes that are reachable from S within the residual graph. So we have been talking about the residual graph instead of the original graph, right? So let's call all the nodes that are reachable from S called A, right? Let's also call all the rest of the node to be B, right? So now we can sort of like it's now you can sort of see that we are heading towards there, right? So we even managed to able to find two sets. One is called A, the other one is called B, right? So basically it's you can sort of imagine that our goal is to find the cut A and B such that the capacity of A and B equal to the value, right? So now we have a very intuitive way of defining A and B. So at the end, right, so we already construct A and B, right? The only thing we really need to do is to verify the statement over here is true for the set of A and B, right? So verify it's true. Fine. Right, so construction, like let me just repeat, right? So let's start with an FF such that it doesn't have any augmenting paths, right? So let's next draw the residual graph, right? So and we know that if we run a BFS or DFS from the S, it's not going to be able to reach T because there doesn't exist any augmenting paths on this residual graphs, right? So in the graph language, it basically means that there doesn't exist any paths that's connecting between S and T, right? So that also means that if I run a BFS starting from S, then the T will be disconnected, right? So after I run the BFS, then I'm able to find all the nodes that are reachable by T, right? So let's just naturally call this A, and let's also call the rest of the nodes B. And then the A and B are exactly the A and B that we are looking for. And then we next really just need to want to verify that the equation highlighted by the blue circle is going to hold, right? So now, let's continue what's the argument coming from the slides, right? So by the definition, S belongs to A because I run a BFS that's starting from S, right? So S belongs to A, right? And then also by the definition of the flow, T doesn't belong to A, right? So that basically means that if T belongs to A, that means that T is reachable from S, which also means that the augmenting path exists, right? So T doesn't belong to A. Right, now we can do a bit of the math here, right? So now we are working on trying to explain all the equality here, right? So value of the flow equals to E out of A minus E into A, right? So this is the flow values lemma, right? Lemma, LEMMA, right? So basically that's what's happening here, right? So it's very early on, right? So this is the flow value lemma, right? So we just apply this lemma and then we sort of know that the first inequality holds, right? So this is the flow value lemma. And the second thing, we sort of want to see prove the equality here highlighted by my red pen, right? So I really want to prove two things, right? So for any E out of A, FE is the same as CE, right? So let me just say why I'm coming up with this statement. I'm going to sum up with all the E out of A of FE, right? So if we cheat a little bit and look at what's the how this is transformed, we sort of know that, well, I'm still looking all the edges out of A, but all of a sudden I translate the FE into the CE, right? So the SF becomes C here, right? So now, then basically I want to prove that for any E out of V, right? So these two statements are the same, E out of the A, right? So I want to prove that FE equal to the CE. Right. So now let's just look at one specific edge, right? So let me just make it a little bit bolder, right? So this is one specific edge that's coming out of A, right? So let's imagine this is not full, right? So let's imagine that what happens, like what happens if it's not full? Not full, right? Not full means that the f of E is say 13 and the C of E is 15, right? So in case this is not true, then basically we sort of have f of E is a bit less than C of E, right? In case this is true, then actually we can sort of see that in the residual graph, right? So in the residual graph, there's actually, so if I look at this node, I draw this node again over here, right? So if there's an edge that's 13 out of 15, that basically means that when I draw the residual graph, there are only two levels of there's still a path, an edge that's connecting from the left node to a node that's in B, right? So let me just erase everything and try to elaborate what I'm talking about here, right? So I'm making the claim that if I look at this particular edge, it has to be, say, for instance, 15 out of 15. If this is not true, so let's imagine that it's 14 out of 15, then the edge, then basically if I look at the residual graph, right? So let's call this as U and let's call this as V, right? So if I look at the residual graph, this is U and this V. I want to decide the weights of two edges from U to V and from V to U, right? From V to U would be straightforward. I can just copy the whole thing, the 14 here, right? From U to V would be 1, which is equal to 15 minus 14, right? That basically means that this edge would have existed in the residual graph, right? So let me just see. Let's again just see what we are doing, right? In case this is not true, we are not fully utilizing all the capacity. Then in the residual graph, the UV edge exists, right? Exists. When the UV edge exists, that basically also implies that V should be in A, right? So this is contradicting to the fact that this is a cut, right? This is an edge that's connecting two nodes. One is from A, the other one is from B, right? So it's contradicting to the statement that E is out of A, right? So the reason that V should be in A is because there's an edge that's connecting between U and V. U is within A, within the set A, and then V should also be reachable. It's still a bit messy, right? Let me just switch to the whiteboard and draw a little bit more to explain this idea, because I think that would... Right, so let's start with, there are three notions here, right? So there's one notion of the original flow network, right? So this is the original network, right? So I'm not going to draw the detail. There's an original network, right? Besides the original network, there's also the existing flow, right? There's an existing flow, right? The existing flow basically says that, well, I'm going to, I decided to push that, so this is S, this is T. I decided to push that amount of flow that's across the network, right? So sometimes I'm not using some of the edges, right? So this is an existing flow. Together with the original network and the existing flow, we can come up with a residual graph, right? Residual graph. The residual graph basically says that, well, just use the rules we have been talking about, right? If it's 7 out of 10, then the residual graph has a 3 on this direction and a 7 on the other direction, right? So this is the rule we are using by constructing the residual graph, right? So somehow I construct a residual graph. I don't know how it looks like, but probably, I don't know, right? So maybe that's how the residual graph looks like, right? So now, so when we say that we want to prove 3 implies 1, right? So this is the condition we want to prove. 3 is basically means that no augmenting paths, right? pass with respect to f, right? So this is our f, right? So we need to fix any f. And then let's assume that there's no augmenting paths. And we want to say prove that that implies the one means that there exists an A and B as a chord such that capacity of A and B is the same of the value of f, right? So this is what we need, right? So now, in case there's no augmenting paths, we can sort of run a BFS, right? So we can run a BFS. Let's run a BFS and pull out all the nodes that are reachable from S, right? So this is what we have been doing. This is S, this is T, and then let me also draw some sort of the things. Let's some edges over here, right? So now I sort of want to say that for any edges, right? So for any edges that's for any edge that's out of A, which means that the edge has two ends, U and V. U is inside A and V is not inside A, right? So for any edge that's out of A, if I look at the flow itself here, then I want to claim that the flow of the edge is the same of the capacity of the edge. This is what we are claiming here, right? So if this were not true, this were not true, and then we want to sort of find a contradiction. How do we find the contradiction? So let's assume there's an edge over here, and then let's say we utilize the 14 out of the 15 capacity, right? This is the capacity, this is the current flow, right? So in case this were correct, let me just pull out this particular fraction, this particular region of the graph, right? So let's look at what the residual graph is going to look like. The residual graph will look like that, right? From U to V, I still can have 1 unit of flow. From V to U, I can have 14 units of flow, right? So basically, if this is not true, then there exists an edge that's connecting from U to V in the residual graph. This intuitively saying that like we can continue to push more flow, right? So this is what's implied here, right? When there's like so now the contradiction is now start to be self-evident, right? When there's an edge connecting from U to V, and as U is reachable from S, then V would also be reachable from S. V would be reachable from S. From S, right? Because we can use S to travel to U, and there's an existing edge of U to V, right? So that basically means that I can use S to travel to V, then basically means that V is reachable, right? But when we say V is reachable, that's actually contradicting to the way we pick up the edge, right? So the way we pick up the edge is that we want to pick up an edge such that U is in A, V is not in A, but at the end we sort of prove that the V is actually in A, right? So that's actually the contradiction we are getting, right? So that's the reason we cannot have the case, right? This equality doesn't hold. It's always true that the f of E equal to the C of E whenever the E is out of A, right? That's the first part, right? So now the second part is that whenever E, so let's go back to the slide. So now let's go back to the slides, right? So I forgot to delete, right? So we managed to prove that it's always true that the f of E equal to C of E so long as E is out of A, right? So FE equal to C of E for any E out of A, right? So now we sort of need to prove that for any E into A, f of E equal to 0. Right. That's also for the same reason that if I look at the residual graph, right? So this is A and this is B. If I look at the residual graph, right? So if there's an edge that's coming inside, right? So let's call this U, this is V, right? So I want to sum up of E inside A and the value of the flow, right? So if I somehow I'm sending say 1 unit of flow out of 10 units, right? So let's say that this is the current status, right? By the definition, the way we are going to build the residual graph, U and V, if I look at the residual graph, it will be something like that, right? Coming back is 9, going out is 1. 1 is the same as the 1 here, right? So I have the luxury of being able to send 1 unit from U to V, right? So that basically means that in residual graph, I will have something like that, right? This is A, this is U, there's an edge coming from U to V, right? And this would be the residual graph, right? So the two edges are talking about the same thing. This also again also implies V is part of A, because U is reachable from S, and then there's an edge. Again, there's an edge U and V, so that being implies V is also in A, right? So that again contradicts to the fact that we pick up an edge that's crossing the cut, right? So both directions are more or less the same, right? So that's the reason that for this component here, we get into 0 as well, right? After we have all both of the component, right? Let's just erase a little bit, right? So we sort of prove that when an edge is going forward, I have to fully utilize that. When an edge is going backward, I have to not use that. Otherwise, E will not be a cross edges, right? So if I use both conditions, I will translate the summation, two summations into a summation and a 0, right? So again, if you look at the summation here, it's the definition of the capacity of A and B, right? So by now we managed to prove that by using the way we construct A and B, indeed the value of F equals to capacity of A and B, and that really wraps up our proof on 3 implies 1, right? So now we all get that 1 implies 2, 2 implies 3, 3 implies 1. So that basically means that we managed to show that all these 3's are equivalent, right? So after we manage to show all these 3 is equivalent, then it becomes trivial, right? So if flow is a max flow, that basically means that if condition 2 is holds, then there's no augmenting path, right? So basically condition 3 also holds, right? 2 implies 3, 3 also implies 2, right? So that's sort of the when that sort of strict becomes self-evident or straightforward when all these 3 conditions are equivalent. Then the augmenting path theorem becomes self-evident, and then you can also check on your own. If we are able to show that augmenting path theorem is correct, the max flow indeed is the same as the mean cut, right? So the max flow, right? If F is max flow, right? Max flow, then basically means that condition 2 is the same as holds, right? Condition 2 holds, condition 1 also holds. That basically means that there exists A and B such that the capacity of A and B is the same as the value of F, right? So, and then after we use the weak duality theorem, that basically means that F, the A and B has also to be mean cut, right? So that basically wraps up the entire max flow and mean cut theorem, right? Let's see, right? So basically this is already done, right? So the next thing the slide is talking about is that if we have a max flow, can we find a mean cut, right? So just by looking at our proof, it seems that when we are given a max flow, we look at the residual graph, we find all the nodes that are reachable from S in the residual graph. That would be our set A, right? So after we find the A, then according to the max flow mean cut theorem, right, the cutoff between A and B would exactly be the same as the max flow, which means that A and B themselves are the mean cut, right? So in other words, so long as we manage to prove them the max flow mean cut theorem, then finding a max flow can be done using the Fulkerson algorithm, and finding the mean cut can also be done by running the BFS of the residual graph, right? So that also sort of gives you a feeling of like the importance of this max flow mean cut lemma or theorem, right? Once you got this proved, then there are a lot of powerful corollaries. So after we have shown the max flow mean cut theorem and the correctness of the Fulkerson algorithm, we sort of need to move back and examine the running time of the algorithm. We will see that if we just run the plain version of the Fulkerson algorithm, there could be scenarios in which the algorithm runs very slowly, and then we need to find a way to address this issue. And then we call that we design a new algorithm, I think, which is based on a minor modification of the original Fulkerson algorithm, and then we can guarantee the running time of the new algorithm is going to be in polynomial time. Right. So before we proceed, right, we sort of want to make a number of assumptions and and also describe a number of pretty obvious results, right? So the assumption we are making here is that every edge capacity is an integer between 1 and c. So here this is a pretty mild assumption because in case it's a fractional number, we can really just say in case the capacity is 1.1, right? There are some capacities 1.1, then we can really scale all the capacity to 11, right? Let me just repeat what I said just now, right? So this is actually pretty mild assumption in the sense that in case, right? So in case there are exists like for instance some fractional capacities, right? So for instance 1.1, 1.2, let's say that there are two edges like with the capacity being 1.1 and 1.2, then we can sort of scale all the capacity by a factor of 10, then 1.1 becomes 11 and 1.2 becomes 12, then all of a sudden it becomes integer. So in general, this is actually a pretty mild assumption on the setup of the problem, right? And now I actually need to start a little bit to actually make this. Our next observation is really just that in case we start with the edge capacity being an integer, then when we run the Ferguson algorithm, then we sort of realize that every time we update the flow function, the flow function is updated by an integer, and the residual capacity is always an integer, right? So just recall that, right? So we start with an original graph, right? So there's an original graph, right? So this is S, and this is T, right? So this is T, right? This is S. And what we did for the Ferguson algorithm is that we find an integer, we find an augmenting path connecting between S and T, right? And then we do an update on this path, right? So now just review. Let's just think about what's going to happen when we do the update, right? So imagine that we do find an augmenting path that looks like that as like V1, V2, and T, right? So say the original capacity like is 3, 2, 5, right? If I take the mean of this 3, right, is 2, then basically what I need to do is that I decided to push 2 units of flow out of this setting, right? So let me just repeat what I'm talking about here, right? So if let's just review what is being done in the Ferguson algorithm. Every time we are going to find a path that's connecting between S and T in the residual graph, and then we are going to try to push a little bit of more flow on top of the existing one, right? So this is a concrete example, right? In case we found the augmenting path that's connecting between S and T and going through V1 and V2, right? Let's just make up some random arbitrary numbers, right? So we want to make sure that numbers are all integer because we start with the integer capacity, right? So integer capacity. So now if all the numbers are integer, then we pull out so what we need to do is to find out the bottleneck, and recall that the bottleneck is really just the minimum of all the capacities, right? In this case, it's 2, right? So somehow we just decided to push up 2 units of flows on top of the existing ones, right? So now when we want to construct a residual graph, it looks like that, right? So basically, if we want to move forward, it's 1, 0, 3, right? So basically it's the 3 minus 2, 2 minus 2, 5 minus 2, right? So, and then we also need to add the reverse edges, right? So it's all 2 over here, it's for the reverse edge, right? So this is really just a repetition of what's the mechanism of the Ferguson algorithm, right? But the key message here is really just that if you look at all the numbers here, right? So if we start with integer, then our operations are all at the integer level, right? So when we update the flow, we are going to push an integer flow from left to right. And when we compute the new residual graph, right, integer minus integer is still going to be integers, right? So that means that that means that like we do have the so-called integrality invariant, which basically says that throughout the whole algorithm, all the edge flow and the residual capacity is always integers, right? So And when the proof here says that it's proof by induction, right? So, but the intuition is really just like this, what we have been talking about, right? That if we start with integer network, then all the operations will be at the integer level, and that's the reason that the flow and the residual capacity will always be integers, right? So now the next thing is, I think it's also pretty straightforward. It's a theorem, and the theorem says that the fault focusing algorithm terminates after at most n times c rounds, right? When I talk a round, right, basically it's each round we find one augmenting path, right? So why this is true, right? So basically the argument consists of two steps, right? The first step is that we first want to argue that the like in every single round, right? Because all the flows and the residual capacity are integers. Every single round, when we found we want to do an update along one augmenting path, then the value of the flow has to be increased by at least one, right? So that's exactly a repetition of the applications of the integrality invariance. We really just need to make sure that in every single round, the minimum operation level is integer. Whenever you want to add something, the minimum unit is 1, right? So each augmentation increases the value of the flow by 1, right? So imagine that we start with a flow that's empty, right? So, and at the end, there are some optimum flow we don't know, right? So, but we know that every round when we want to update the flow, the value of the update is at least 1, right? That basically means that the number of updates, right? So basically, from the argument here, we sort of see that the number of updates it's going to be at least at most as large as the value of the flow, right? So that's the first part. The number of augmenting paths that's needed is at most the value of the flow. That's the first part of theorem. The second part of theorem says that the value of the flow can be bounded by n times c, right? Why this is true? It's really just that if you look at the graph over here, this S and T, right? So you want to push out. So what would be a very, very loose upper bound, very conservative upper bound of the amount of water you can push from S to T, right? And upper bound basically says that for whatever outgoing edges, I'm going to push out at exactly C unit of flow, right? So let me just maybe I need to switch back to the whiteboard to deliver this idea. So